Good afternoon, everyone. Welcome back. I'm Steve.
And I'm Scott.
Together, we're Backyard Music in the Backyard, Apple Valley.
Yep, and it's a beautiful day, been a beautiful day, and we're ready to get at it.
Yes,
so here
sir.
we go.
The neutral atom platform appears promising for scaling up quantum computers. To solve some of the toughest challenges in physics, chemistry, and other fields, quantum computers will eventually need extremely large numbers of qubits. Unlike classical bits that only represent a 0 or a 1, that's everybody knows that. Qubits can hold both states at the same time through a phenomenon known as superposition, like entanglement. This unusual property of quantum mechanics could allow quantum computers to outperform traditional machines in certain types of calculations. However, qubits are highly delicate, and this fragility makes them prone to errors. To overcome this, researchers design systems with extra qubits that act as backups to detect and correct mistakes. As a result, building reliable quantum computers is expected to require hundreds of thousands of qubits.
So we can't beef up these qubits to make them less fragile?
Well, we are. I mean, technology is expanding. I mean, you remember when, like, the bits per second used to be 4,400, then 8,800, then 16,000, whatever. And now we're into terabytes, right? I'm sure it's going to be the same for quantum, I think.
Okay.
Would you like to know more?
In a major step towards this goal, physicists at Caltech have assembled the largest qubit array ever achieved. 6,100 neutral atom qubits arranged in a grid using laser light.
Ooh.
Okay. For comparison, earlier versions of similar arrays were limited to just a few hundred qubits. This achievement comes during a rapidly intensifying global race to expand quantum computing. We've talked about that many times, right?
Mm-hmm.
Competing efforts include platforms based on superconducting circuits, trapped ions, and neutral atoms. The approach used in this new study. Okay.
Quote, "This is an exciting moment for neutral atom quantum computing," says Manuel Andres, professor of physics at Caltech. Continuing the quote, "We can now see a pathway to large error-corrected quantum computers. The building blocks are in place," Andres is the principal investigator of the research published in Nature. 3 Caltech graduate students led the study: Hannah Manesh, Gyohai Nomura, and Ellie Batel.
How do you pronounce that guy's first name? Or lady's first name? Whoever that
Ellie? Gyohai Nomura.
Okay. The team used optical tweezers, highly focused laser beams to trap thousands of individual cesium atoms in a grid. To build the arrays of atoms, the researchers split a laser beam into 12,000 tweezers. How could you control all that? Which together held 6,100 atoms in a vacuum chamber. Quote, "On the screen, we can actually see each qubit as a pinpoint of light." Manetish says, "It's a striking image of quantum hardware at a large scale."
Okay. To answer your question, Scott, you'd need 24,000 fingers or 12,000 thumbs and 12,000 fingers to control this.
Okay.
A key achievement was showing that this larger scale did not come at the expense of quality. Even with more than 6,000 qubits in a single array, the team kept them in superposition for about 13 seconds. Wow. 13 seconds, that's a lot, man.
I guess.
Nearly 10 times longer than what was possible in previous similar arrays, while manipulating individual qubits with 99.98% accuracy. That's good. Quote, "Large scale with more atoms is often thought to come at the expense of accuracy, but our results show that we can do both," Nomura says. "Qubits aren't useful without quality. Now we have quantity and quality."
Okay, now we're talking. That's a cell switcher, right?
Mm-hmm.
The team also demonstrated that they could move the atoms hundreds of micrometers across the array while maintaining superposition. The ability to shuttle qubits is a key feature of neutral atom quantum computers that enables more efficient error correction compared with traditional hardwired platforms like superconducting qubits. So hardwired, that's like what, Cat5 stuff? Is that what we're talking about?
Yeah, well, I mean, it's like if you're talking on a chip or something like that,
So
it's
the
very
cable.
tiny. Yeah.
Okay.
Like nano, yeah.
Okay.
Manesh compares the task of moving the individual atoms while keeping them in a state of superposition to balancing a glass of water while running. That's tough. Or carrying that egg on the egg run.
On a cup.
Yeah.
Or on a spoon.
Yeah.
Yeah.
Quote, trying to hold an atom while moving is like trying to not let the glass of water tip over or the egg fall off. Trying to also keep the atom in a state of superposition is like being careful to not run so fast that water splashes over, she says.
Disqualified, right? If that
Yeah.
happens.
Yeah.
The next big milestone for the field is implementing quantum error correction at the scale of thousands of physical qubits. And this work shows that neutral atoms are a strong candidate to get there. This is a quote. Quantum computers, quote, will have to encode information in a way that's tolerant to errors so we can actually do calculations of value. Batil, is that how you pronounce that? Batil says, unlike in classical computers, qubits can simply be copied to do the so-called no cloning theorem. So error correction has to rely on some subtle strategies. Unquote.
Looking ahead, the researchers plan to link the qubits in their array together in a state of entanglement, where particles become correlated and behave as one. Entanglement is a necessary step for quantum computers to move beyond simply storing information in superposition. Entanglement will allow them to begin carrying out full quantum computations. It is also what gives quantum computers their ultimate power, the ability to simulate nature itself, where entanglement shapes the behavior of matter at every scale. The goal is clear: to harness entanglement to unlock new scientific discoveries, from revealing new phases of matter to guiding the design of novel materials and modeling the quantum fields that govern space and time, to infinity and beyond.
Okay, bring it on. Quantum qubits. That's what we're looking for.
Thanks, folks. We'll see you. Have a great Sabbath. We'll see you on
on Monday. Yeah. Enjoy your rest of your weekend. Thanks.